Hey guys, Diego TA here. It's been a while since my last video. Sorry for the delay, I got caught up in work and doing research. But one of the sort of research problems which I encountered recently was really interesting, and it's a problem I wanted to share with you and sort of even think might be interesting to the larger community. It has to deal with softmaxes. And typically we don't really think too much about the softmax in a machine learning model. It's kind of always trained end to end. And in sort of doing research, like thinking about softmaxes and better ways to do softmaxes or different ways to divide them, with the hopes of improving upon sort of this typical softmax paradigm, I started to ask myself what the softmax was actually optimizing for. So, sort of the end-to-end process of training a model for machine learning, you're optimizing the model to basically output the class probabilities. So you're basically getting an example input and you're outputting a probability distribution across every single class. And that sort of begs the question, what are the logits actually optimizing for then? So if the output of the model is the probability distribution across all the classes, what might the logits be optimizing for? And very simply, in today's sort of short YouTube video, I'd love to show you guys mathematically what the logits are doing. So to begin, maybe we have a machine learning model and it might be taking in an image, for instance, like a 9 or like a 0 or a 1, sort of like an image of a digit if we're talking about MNIST. And typically we have a couple convolutional filters. Maybe if you're more advanced, you're using a vision transformer, which is a little bit of overkill for MNIST, but props to you. And you're sort of constructing this feature extractor. Maybe you have like some feed-forward layers. And if you're doing an LNF5, which is one of the original architectures used for MNIST, one of the very early sort of computer vision architectures, you're going to output a 1 by 84 dimensional vector. And the input, for instance, is going to be 1 by, I think it's 23 by 23 by 1. So you have like a 23 by 23 image, and there's one channel in that image because it's a grayscale digit. And the feature extractor is basically learning this 84-dimensional representation of an image. So you're basically going from this 23 by 23 by 1 sort of representation all the way down to a 1 by 83 dimensional representation, or 1 by 84 dimensional representation. And then you have this funny layer here called the softmax. And the softmax layer is very interesting. It's going to be uh, 84 by the number of classes. So for example, in MNIST you have 10 different digits you're choosing among, 0 all the way through 9. So it's just going to be, sure, you can basically just think of it as a stack of 84-dimensional column vectors. And you have 10 of these for MNIST. So this is going to be 84 by 1. You have 10 of these. And what you're going to do now is you're going to take the output learned representation, sort of the pre-logits from the model, and you're going to do the dot product similarity with every one of these sort of 10 softmax vectors. And you can think of the softmax vectors as essentially being a class embedding. So you have 10 classes, 0 through 9. And each of these sort of column vectors corresponds to sort of the representation of a given class. And that's because when we have this 1 by 84 vector here, and this is going to be the model representation. We're going to take the dot product between these two vectors. And when we take the dot product between an 1 by 84 and an 84 by 1 vector, that's going to give us our first value. And this is going to be a value representative of the probability that this example belongs to class 1. And when we, and I'll sort of get to that statement more later on and sort of prove, oops, a little too eager about the iPad stylus, but sort of prove why that's the case later. But just for right now, you can think of this sort of comparison as comparing the learned representation of the model by every single column in your softmax matrix. And we're comparing them, we're sort of comparing their similarity just by taking the dot product between these two vectors. So we have C1, C2, C3, where C3 is this third orange line right here. And we're going to have 10 of them because we have 10 of these softmax column vectors, because this is a 84 by size, the number of classes. And we'll just very quickly define here the size of the number of classes is equal to 10. So C10. And this is what we call the logits. So after you compare the learned representation, or sort of this extracted feature representation, where you basically have this image and then you're doing an affine transformation, and you're taking nonlinearity, which is essentially sort of projecting into latent space, and then you're projecting into smaller latent space, and you sort of keep rearranging the data into the space, and you're finally doing a sort of dot product similarity comparison between the class embeddings, which are, once again, these sort of softmax columns. So you're saying, here's my class embedding. This 84-dimensional vector is sort of representative of my class. This is like the quintessential sort of class representation. We're going to do a dot product similarity between what the model sort of learned, what the model extracted from this given image, with each of the sort of class embeddings. And we're going to then use that information, sort of that similarity information, to actually construct a probability distribution across all classes. And sort of taking a step forward, the name of the sort of vector after we take the dot product, the similarity sort of dot product, the similarity measurement, which is the dot product between the learned representation and the column vectors, is called the logits. So this sort of value right here are the logits. And this is going to equal a 1 by 84 representation, and we're going to matrix multiply it with an 84 by size C matrix, and we're going to get a 1 by size C vector out. And we know size C is going to equal 10. For this example, we have 10 different digits between 0 and 9. So what we do next in sort of the typical machine learning paradigm is we take the softmax of the logits and we just say that gives us the class probabilities. Awesome. I think I'm going to leave it there, since I really want to make these videos not too long, and I'll probably have a part 2 and maybe even a part 3 depending on how much I ramble. But the thing I really sort of want to leave you with for this particular first video is that you can really see the model in 2 stages, where you have this first stage of feature extraction, changing the basically basis vectors of a space and sort of reducing the number of basis vectors to learn a latent representation of your data, which is then linearly separable by taking the dot product similarity between the learned representation and the columns in the softmax matrix. So it essentially has sort of 2 stages to this model, like the non-linear sort of feature extractor, followed by this very well-defined softmax function and sort of dot product combination to determine which class is most similar to the learned representation. So hope to see you guys in part 2, where we sort of go into cross entropy a little bit more and then work our way back from cross entropy to the softmax to the logits. And I hope you guys find this helpful. Cool. See you around.